Welcome to your online lesson. Today we're going to be talking about trig ratios, starting a new unit, and we will be using trig ratios to solve for missing sides of a right triangle. We will know we are successful when we can solve right triangles using trig ratios. So there's three trigonometric functions that we looked at last class or last lesson, and those include sine of an angle, which is opposite over hypotenuse, cosine of an angle, which is adjacent over hypotenuse, and tangent of an angle, which is opposite over adjacent. If you're unsure about what any of these mean, go back to our previous lesson because those were all covered there. A quick reminder that we use the acronym SOHCAHTOA to remind ourselves what those ratios or functions are. So the sine is the opposite over hypotenuse, which we can see right here. And the cosine is adjacent over hypotenuse, which we see here, and tangent is opposite over adjacent. So when I do these problems with our next two examples, you'll notice that one of the first things I do is write down SOHCAHTOA just so I don't mess up forgetting what the different ratios are when I'm setting up my equations. So our first example, we are going to correct to three significant figures, the unknown length, or x, in the following triangle. So what do we have here? We have one side that's labeled 7 centimeters. We have another side that they've gone ahead and labeled x to let us know that that's what we're looking for. And then they've given us one angle, one of the non-right angles, and then of course we know it's a right triangle, so we know that it has a 90-degree angle as well. Now if this was a triangle where they gave us two sides, and then we had to find x, we could use Pythagorean theorem. Unfortunately, I don't know the third side, plus we have this missing value here. So we can't use Pythagorean theorem. That's why we need a new technique, and we're going to use our trig ratios or trig functions to set up an equation and solve this. So since we're dealing with trig ratios, again, I'm going to write down SOHCAHTOA. So sine is opposite over hypotenuse, ka, adjacent over hypotenuse, toa, tangent is opposite over adjacent. And we need to start with our angle, our non-right angle, which is 32 degrees. And so comparing to that 32 degrees, what do we have with this x side and this 7 centimeter side? Well, right away, I can see the 7 centimeters is a very special side. It's our hypotenuse. So one of the ratios that we have to deal with has to involve hypotenuse. As I look at these with SOHCAHTOA, one of them doesn't involve hypotenuse or have an h, and that would be the tangent. So right away, I am getting rid of TOA, or the tangent function. So I like possibly sine, I like possibly cosine. Now I need to look at the other side. So again, going back to our 32-degree angle, we have this other side labeled x. Now if it was across from it, we'd say it was opposite, but I don't know that side. So we need to go and think about what this means when it's next to it, and that's the one that we call adjacent. So we have sine, which has opposite and hypotenuse. Well, we have a hypotenuse, but we don't know the opposite side, so we're getting rid of that one. And then we're left with cosine, which is adjacent and hypotenuse, and that's exactly what we have. We have the adjacent side, which is x that we're trying to find, and then we have the hypotenuse, which is 7 centimeters. So we know we're going to use cosine, so I'm going to start off by writing COS, abbreviation of cosine, and we always do cosine or sine or tangent or any of our trig functions is always of an angle. Well, what non-right angle do we have? We have 32 degrees. Now you can put the degree symbol down, you don't have to, but it is dealing with 32 degrees. And cosine, remember, is equal to AH. Well, what does the A mean? That's the adjacent. So the adjacent has to go on top. And again, if we go back and look at this 32-degree angle, which side was adjacent? That was the one labeled x. That was the one next to it. And then we have the hypotenuse, which we know is 7 here. So we're going to have x over 7. And that's similar to what we did in our previous lesson where we just set up the trig ratios or trig functions. Now we want to actually do some railroad track algebra and solve this. Now, a quick reminder here, two things to keep in mind. We are dealing with degrees in this class exclusively. There's another way to measure angles called radians, but we're not using that. So if you go to your TI calculators, hit the mode key and make sure that it is in degrees. Again, mode, and then select degrees. Make sure that your calculator's in that mode since we're dealing with degrees in this angle. Second thing to keep in mind is I am not going to even reach for my calculator until the very last step of this equation. So I'm going to do my algebra working with the words, cosine, the abbreviations, the acronyms, all that stuff, and I'm not going to reach for the calculator until the very last step. All right, so now thinking about algebra, we have an x that we want to get alone. Our question is, what is happening to this x right here in my equation? And currently we can see that it's being divided by 7. So what opposite operation do we want to use to get rid of division by 7? And that would be multiplication. So I'm going to put parentheses around both sides of my equation. And since I want to get rid of the 7 on the right side that was dividing the x, I'm going to multiply by 7, and those will cancel out. That was the whole goal. But whatever I do to one side, I have to do to the other. So now you don't really need to rewrite this, but I will just so it's clear. We have 7 times the cosine of 32 degrees. And that is equal to x. So that's my answer. It's just that it doesn't really look like a length, a certain number of centimeters like x is. So now is the time that we reach for our calculator. So I'm, again, going to make sure that my calculator is in degree mode. And then I'm just going to type 7, parenthesis, cosine. It'll automatically open another parenthesis. I can put in the 32. And then ideally, I should close both of my parentheses, though the calculator probably will let it go even if you don't. And we get a final answer of x is approximately 5.94, and that is centimeters because we are finding a length of our triangle. Again, that's rounded correct to 3 significant figures. All right, and then if we look at it, it should certainly be less than the hypotenuse that we had, which was 7, and it is less than it, but not a ton less than it so that it looks ridiculous. So that seems like a reasonable answer based on the picture and what we know about triangles in general. All right, we're going to do one last example here. For example 2, once again, we're finding correct to 3 significant figures, the unknown length, which is labeled x, in the following triangles. So this time we're dealing with meters. We have an angle, a non-right angle that is 64 degrees. Once again, they only give us one length of side, this 5 meters here, so we can't use Pythagorean theorem. And so what we want to do is we want to think about which trig ratio is going to work best for us here. Sine, once again, is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Well, rather than eliminating this time, let's think about what we actually have. If we look at the 64 here, we have the 5, which is across from it, or opposite. And then we have the x, which is not the hypotenuse, but is next to the 64-degree angle, or helping to form that 64-degree angle. So we would call this one the adjacent side. So we need opposite and adjacent. Nope, nope, yes. Tangent is opposite over adjacent. So we're going to have to be careful about what order we put these in, but we know we're going to use tangent. So I'm going to start by writing my trig function, or trig ratio. I have tangent, and again, we always do sine, cosine, or tangent of an angle. So it's going to be tangent of 64 degrees. Again, if you leave off the degree sign, it's not a big deal. So tangent of 64 is equal to, now double check, it's opposite over adjacent. So we're going to put the 5, which was opposite of this angle of 64 degrees, and we're going to put that over our adjacent, which is x. All right, so once again, we have our equation set up, very similar to what we had done in our previous lesson, but now we have to go back to doing some algebra and solving for x. Now, if you take a moment and look at this equation, x is not in the place we normally like it to be as far as a fraction goes. It is in the denominator, and we want to get x out of the denominator. So the way I do this is I will often just multiply both sides by an x. And what that'll do is it'll cancel out those x's that we have over on the right side, leaving just a 5 there. And then on the left side, I have an x that's no longer in my denominator, but it is getting multiplied by this trig function, essentially, or trig stuff. And so we have x times the tangent of 64 degrees equals 5. Well, that's a little bit closer to what I want, but I still want to know what x itself is. I want to know how big this side is. So I need to get x alone. In order to get x alone, I need to undo whatever is happening to x. Well, these parentheses around tangent of 64 is indicating that we are multiplying that by x We need to undo that multiplication. In order to undo multiplication, we divide. So I'm going to divide this side by tangent of 64, and I'm going to multiply the other side by tangent of 64. Now that looks funny. We're not used to doing algebra or division with words and abbreviations like tangent and things like that, but we're still just doing the same thing. We know that tangent of 64 is a number when we punch it in the calculator. The reason we haven't done it yet is it's going to come out to some very long decimal, and I don't want to round until I get to my last step. So on the left side, since we divided both sides by tangent of 64, x is the only thing that's left. On the right side, we have 5 divided by tangent of 64. I punch that into the calculator, and I end up with 2.44. And again, let's think about what this is. It's an actual side. It's x, so we can label that with meters. Again, looking at our triangle, it should certainly be less than the hypotenuse. And the other leg that we had was 5 meters. This one looked to be about half if the picture was to scale, which I'm not even sure that it is, but it's a reasonable length. It's not ridiculously small, and it's not too big either. And so we have solved for a missing side of this triangle. All right, and that concludes our lesson. Till next time.